Hello, my name is Traber Shears, and this is my presentation for my final project in real-time systems. So for starters in this, I'm going to talk a little bit about what the project I chose is. I'm going to talk about what we've learned in real-time systems and how that applies to the project I chose. I'm going to give a short demonstration of my final product, and then I'm also going to talk about what I could have done along the way and what I would like to do now, kind of looking back on it, that could have possibly improved the product as a whole. So what is my product? My product is called Spek. Spek is an at-a-glance calendar system that you could put outside your door of your room, maybe of your office, and it's just a quick display for people to look at and figure out what's going on with you. So if you're in a meeting, it could say, like you see on the screen, say busy. It tells you how long you have left in that. If you are currently free, it tells you how long until your next event will start. So you can look at that and you can see kind of how much time somebody has. If they need to have a long conversation, they need to ask about something, they can pick a good time to do that. In terms of the features, it's got that adaptable digital display. It's got a digital clock on it, which can change size because of the way that display is set up. It has a real-time calendar link, so it will talk to your actual Google Calendar, and it also has that event countdown, so you can see either how long until the end of your current event or how long until the beginning of your next event. In terms of the real-time systems features, it uses a first-come, first-served scheduling algorithm. It talks to the Google Calendar API that took so long for me to set up, and I'm so proud that I was able to do that and get that figured out. It talks to the real-time clock server, so it's got accurate time down to the millisecond. And then it also has a Wi-Fi connection so that you don't have to have a long cable run into it if you wanted to use it practically. In terms of the onboard functions, it has to do everything from update the screen to parse the JSON file it gets from Google and figure out what order the events occur in and how long each of those events is to make sure that it can schedule them properly. So it has to maintain its own local schedule. It has to obviously maintain its Wi-Fi connection, maintain its connection with the clock. So there's a lot of stuff going on, and making sure that it all can occur in the right amount of time is what the real-time systems is all about. So in terms of what worked that I was able to complete, everything is organized into functions within the C++ Arduino language, right? So you've got the Wi-Fi, which constantly wants to be updating. You've got the real-time clock, which is accurate to the millisecond and wants to be updating. The screen always wants to be updating. And so because all those things are kind of fighting over your resources, I had to find a way to get them all to play nicely. Each of the functions, they're pulled out of Arduino libraries and kind of put together, but they all want all of the time to themselves, and that's just not possible. In terms of things that didn't work, the Google API, like I said, it took me so long to set it up. Apparently security is a thing, and getting through security takes ticks. It takes milliseconds. It takes time to actually access the data that you're trying to get to. With a big company like Google, it shouldn't have been surprised that it took me as long to figure that out as it did. But going through that process and working with some of my friends, working with some of my online resources was a really fun way to kind of bring some of the practical stuff into what I've learned. In terms of the screen refresh rate, I finally was able to find a screen that didn't need to constantly be talking to. So the way that this screen that I chose works is it will remember whatever you tell it. I don't have to constantly be pushing and telling it what's going on. So it looks like it's real time. The clock updates and looks like it's in real time, but in reality, there's a huge gap between when it's actually receiving data and it's flashing that LED to make the screen look like it's lighting up, which is awesome. Schrodinger's clock. So to figure out how long each of these functions took, I had to set up functions to observe that. But what I kind of failed to realize is that in doing that, that also took ticks. So tracking what the average time a function was taking ticks to compute. And I ended up probably kind of skewing my data, but there's no way I could have that without doing that. So while some of the stuff I'm going to show you here in just a second might be a little bit off, this is the best I could possibly do to figure it out. All right, so here are my 5 main processes. It starts with connecting to the Wi-Fi. So that's very important. I can't do anything if I can't talk to the internet. Took about 41 milliseconds. That's right in the middle of the road for my shorter functions. Being able to set that up took the longest amount of time. Actually establishing the connection takes about 6 seconds, and then the router wants to make sure and check that everything's good, and then you can actually start accessing data. If you try to do it sooner than that, you're a little too quick, then a lot of stuff will fail, and it kind of cascades down the line and ends up delaying everything even more. So while the initial setup is about 6 to 8 seconds, once you get it going, the actual check-ins with the router and everything are nice and short. Average is about 41 milliseconds. In terms of contacting the clock, that actually took a little bit longer, or sorry, a little bit less time than I thought it would. It's talking to just the local real-time clock server. It's pulling the Unix format, or it's called epoch time, which is something else that I learned about while figuring this out. Had no idea how computers kept track of stuff, but I guess it's just setting an arbitrary date of January 1 in 1970 and rolling with it from there works for whatever applications you've got. The next two are obviously a lot longer than the other three, and that's because they are what's contacting stuff over the Wi-Fi. So the longest thing is the Google API. Like I mentioned, it takes some time to get through that security, so it's no surprise that that's way longer than all the other stuff. And then, of course, it has to also transmit that huge data file back with all of my calendar events. I found a way to narrow that down by limiting the dates that it's pulling from. Instead of pulling my entire calendar, it only has to pull 24 hours from, I had it go an hour previous to the end of the next day. The next function is also a little bit longer, and that's actually processing that JSON file that it gets back and making sure that all the events can be organized locally. Once you get the JSON file, I don't want to be referencing that forever because all the other functions need to have their time to run as well. So instead, I have a local event manager, and that has to be sorted. The events have to be validated before they can be entered into it, and running that just takes a lot of time. The shortest task, of course, is pushing to the screen. So like I said, once I found that screen that was able to just take it, I can just wait until I got everything ready to go. I can update once a second, and it looks exactly the same. So I actually update about 3 or 4 times a second just to make sure that if something gets messed up, there's some extra time in there. But because humans are so slow, you can't really tell the difference. 32 milliseconds is practically nothing at all. All right, I'll go ahead and get into a little demonstration. Alright, so here's our digital display. You can see how small it is by comparing it to the size of my pinky nail right there. It's hooked up to an Arduino MKR Wi-Fi 1010 so that it can communicate wirelessly. Now, let's go ahead and look at our schedule over here. As you can see, Barnite and Hyperov Show are on my schedule, but they're not showing up because it's only looking ahead until 1 a.m. the next day. Now, let's say at today, I'm going to go give a presentation at 4 o'clock. There you go. In 13 hours, I have a presentation. Maybe I want to move it up an hour. 12 hours, I have a presentation. What about what I'm doing right now? Right now, I'm working on my video. Now, that's higher up, so it's going to take priority, and it's going to update the screen to say that I'm busy for the next 17 minutes. All right, now maybe a little bit I'll get to sleep. That'd be pretty cool. That's not going to change anything because it's still lower than the video in priority. Now, let's say the video time has passed. Oh, not quite. There we go. Next thing up on my schedule is sleep. Okay, so maybe I'm still working on the video. I'm not going to get to sleep. Instead, video is going to take me a really long time. Now it doesn't end in 16 minutes. It ends in 3 hours. That would be very unfortunate. Now maybe that goes away. I'm done with my video. I have the presentation, but you know what? I'm not going to go to that. I'm going to sleep for another 14, 15 hours. So, nothing will be on my schedule. All right, so that's super cool. And now I'm going to talk a little bit about some of the things I could have done along the way to make this better or run a little bit faster. So, for starters, I should have used either the EDF or the rate monotonic scheduler. Those are super complicated to implement, and I didn't think that I would need to do that. But in reality, first come, first serve just doesn't quite cut it. Everything that has to happen like I said, they're all fighting for their separate slots to run. And having them come in first come, first serve means I just have to wait. There's just a lot of waiting, and sometimes stuff will miss its deadlines because of that. So if I had to do it again, I would have throw the whole thing in the trash and build it again from the ground up using either the EDF or that rate monotonic scheduler. Making the functions more efficient is kind of an obvious one, but writing the code, it's always like that, right? If you can cut a couple milliseconds off, you can cut a couple lines of code out, you will save time. The longest function was that 600 something millisecond one where I have to sort the events. I know that could be more efficient. I'm using bubble sort. The fact that I did that because it was easy to implement, but honestly, if I had to do it again, that would be one of the easiest things to cut the time down on, and because that's such a large function, that could save me a pretty decent chunk. And finally, storing the time on board wasn't something I had originally considered. The Arduino keeps track of its own clock. So what I could do is I could have pulled in the Unix time and just remembered that on board the Arduino, and then just maybe do a sync once a day or something, so that it does make sure that it's staying on the right time and that it's accurate with that clock. But otherwise, the fact it has to contact the server so much would be another big chunk that I could cut out that would help me save some time. All right, so in summary, this is a great tool. I'd love to try to polish it off a little bit and maybe push it out to some other people and see what they think about it, see how they can use it, and possibly even get it published as like a Kickstarter product or something. But I had a lot of fun learning how to make this. Getting through all the APIs and learning about the time was very, very interesting for me. And the challenges, of course, that come with implementing anything you learn in class in the real world or in a practical application helped me learn a lot about all the different real-time system stuff. So with that, thank you very much for watching my presentation. I appreciate it, and I will see you tomorrow in class.